Hello, welcome everyone. In today's lecture, we are going to start something completely new, which is called energy methods. And these energy methods are actually very helpful in finding out displacements and deflections and rotations. So if you think about what you have done in the most of the class so far, we have been mostly looking at stress. Okay? We have not worried too much about strains or deflection. So from this class on, for the next few lectures at least, we'll be looking at how we are going to find out the deformations or the rotations or the twist that you apply to materials when you deform them via bending or axial deformation or torsion. Okay, so that is what we are going to learn today. So what are the objectives of this class? So we are essentially going to focus on three objectives. The first thing is that we are going to learn how to determine the work done by forces and moments. Okay, then we will learn a new concept called strain energy, and then we will find out how to calculate the strain energy due to bending, torsion, and axial deformation. And the last thing that we will do is we will use the equivalence between work done and the strain energy in the body to calculate deflections, rotations, and so on. Okay? And then we will also look at what are the limitations of the method that we are going to learn. Okay, so let's just start with a very simple example to figure out what is the work done by a force or a moment. Okay, so in this case, let's think of a bar of uniform cross-section in which you slowly increase the force from 0 all the way until its final value P. Okay, and let's assume that during the process where you raise the force from 0 to P, the bar extends by a distance delta. Okay, so initially the bar had some length, now it is longer by a length delta. Okay, now how do you calculate the work done by this force P? Okay, we know that an infinitesimal work done, dW, is F times dx. Okay, now if you want to calculate the total work done, what you have to do is essentially integrate this expression from 0, which is the initial deflection or initial displacement, to the final displacement, which is delta. So essentially, the work done by this force is going to be integral from 0 to delta of F times dx. Okay. Now, if you make the assumption that this material is linear elastic, what do you mean by that? If it's a linear elastic material, then the force is nothing but some spring constant times the displacement. So F is going to be K times X. And this K is nothing but the final force P over the final displacement delta. So K is P over delta. So essentially, your work done is going to be integral 0 to delta of Kx dx, but K is nothing but P over delta. So essentially, you can pull that term out and then integrate x dx from 0 to delta, and that turns out to be nothing but delta square divided by 2. Okay? So essentially, if you find out what is the work done by this force P, it is going to be half P times delta. Okay, it is not P times delta, it is half P times delta, because your force is increasing over time and eventually you reach the final force P. Okay, and similarly, the deflection is 0 to start with, and finally you end up with the deflection delta. Now, let's take this bar that has already been deformed by this force P and now add an additional force P prime. And again, I am going to slowly increase the value of P prime from 0 to its final value of P prime. Okay, so what happens then? So initially, you already have this deflection delta. Now I am going to pull it even further using this force P prime. And again, P prime, I'm going to slowly increase, okay, from 0 to its final value. Now, if you look at what is the total work done now by P and P prime, it is going to be slightly different, because when this deflection was increasing by this delta prime, the force P that you are applying is constant. In the earlier case, the force was also slowly increasing with the deflection. In this case, the force P is constant. Only the force P prime is increasing. Okay? So, how do you calculate the force or the work done by both these forces? The simple way to do it is actually to draw the force versus displacement diagram. Okay? So initially, if you think about it, you are slowly increasing the force from 0 to P. That is the first force. And the deflection corresponding to that was delta. So this shaded area here, that is the work done by the force P initially. Now, after this force caused a deflection delta, you applied an additional force P prime. So now the total force is increasing like this all the way to P plus P prime. Okay? And the deflection is going from delta to delta plus delta prime. Right? Now, if you look at the additional work that is done now, it is essentially this area here. In that area, this rectangle is the work done by P. And this triangle here is the work done by P prime. So the work done by P prime is half P prime times delta prime. Whereas the work done by P during this process, the second process, is P times delta prime. Okay? So the main thing that I want you to notice that if the force is changing with the displacement, then essentially you have to integrate f dx. Okay? If the force is constant and the displacement alone is changing, then the work done by that force is the constant value of that force times the total displacement. Okay? So that is how you calculate the force, the work done by a force. Similarly, you can also calculate what is the work done by a moment or a coupled moment or a concentrated moment. So essentially, if you have a body and then you apply a moment m0 and that causes a rotation theta, then the work done by that moment is half m times theta. Okay, so or half m0 times theta, whichever way you want to look at it. Okay, so similar to the work done by the force, which is P times delta, half P times delta, the work done by the moment is half m times theta. So the force and displacement are complementary variables. The moment and rotation are complementary variables. Okay? But the form of the work done equation is pretty similar. Okay, so that is the work done by the force and moment. Okay, now we are going to look at what happens to the body when you apply a force or a moment. Okay, and that is what is related to the strain energy. So here again we are going to look at something very, very simple. We are going to look at an infinitesimally small element. Okay, that I have drawn here. Okay, and this small element has dimensions dx, dy, and dz. And I am applying only a single normal stress, sigma z, on this element. Okay? Now, when I apply a stress sigma z on this element, the element is going to extend in the z direction. So essentially, it is going to have a strain. Okay? Now, the force that is related to this sigma z is nothing but dfz, which is the stress sigma z times the area on which it is acting, which is nothing but dx times dy. Okay, so that is the force that is acting on this infinitesimally small element. Okay, and what is going to be the displacement of this element, or what is going to be the deflection or the deformation of this element? That is related to the strain. Okay, so the strain is nothing but sigma z over E, which is the Young's modulus, right? But we will get back to that a little bit later. But let's just look at the strain to start with. The strain, if it is epsilon z, then the total deformation is given by epsilon z times dz, because dz is the original length of the element in the z direction. So delta z, the change in length, is going to be nothing but epsilon z times dz. Okay, so that is what I have written here. Okay, so if you want to find out what is the work done by this dfc, we again are going to use the same formula. It is half f times delta, so it's going to be half dfz times d delta z, and that turns out to be this. Okay, so it is half sigma x times dx dy times epsilon x times dz. Okay, now we can essentially pull all these dx, dy, dz together. So essentially it becomes half sigma z times epsilon z times dx, dy, dz. So what is this dx, dy, dz? Dx times dy times dz is nothing but the volume of the small element, which is dV. So that is the volume of this element. Okay. Now you start to see something interesting. The work done by this dFc is essentially related to the stress in the element and the strain in the element and the volume of the element. So it's half sigma z times epsilon z times dV. Okay? So that is how the strain energy is defined. Okay? Now, if you think of this case, this force Fz is doing some work on the small element. Okay? Now, if there is no dissipation, so if there is no losses due to heat, for example, then whatever work that you do on this element is going to be stored in this element as strain energy. So the internal energy or the strain energy, which is usually denoted by the symbol Ui, is given by dUi equal to half times sigma z times epsilon z times dV. Okay? Now, this half sigma z epsilon z dV is the strain energy stored in this extremely small element. If you want to find out what is the strain energy stored in the whole body, then you have to integrate over the whole volume. Okay? And that is what I have done here. So the total internal energy or the strain energy stored in the body is the integral over the volume of the body of sigma times epsilon divided by 2 times dV. Okay? Now, if this material is linear elastic and isotropic, then your epsilon is nothing but sigma over E. So essentially you can use that in the integral and you can come up with an expression for the internal energy as the integral over the volume of sigma square over 2E times dV. Okay? One thing that I want you to note here is that this formula is true for uniaxial loading, which means that there is only one stress. Okay? In this case it was sigma z. So I dropped that subscript and just put it as sigma. Okay? But this expression that I have derived here is only true for uniaxial loading, where there's only a single normal stress. Similarly, you can also find out what is the work done or what is the internal energy of a body if it is subjected to just one shear stress. And that has a formula like that. Okay? It is tau squared over 2g times dV or tau times gamma divided by 2 times dV. Okay? So g here is the shear modulus, gamma is the shear strain, and tau is the shear stress. So if you look at expressions 1 and 2, they're actually very similar. So in the first case, you have a normal stress and the Young's modulus. In the second case, you have the shear stress and the shear modulus. But the form of the expressions is actually very similar. Okay? But this again is true only for the case where you have a single normal stress or a single shear stress. However, you can generalize this expression for a multi-axial loading or a general state of stress. And that is what we are going to look at next. Okay? Now, if you look at the strain energy for multi-axial loading or a general state of stress, it is going to be a little bit more complicated, so I'm not going to derive it, but this expression number 3 essentially gives you that formula. So the internal energy or the strain energy when you have multi-axial loading is again going to be the integral over the volume. Again, you have a factor half outside the whole thing. And the integral is going to be sigma x times epsilon x, sigma y times epsilon y, sigma z times epsilon z, and so on. And then tau xy times gamma xy, tau xz times gamma xz, and tau yz times gamma yz. And I want you to notice that this is gamma, which is the shear strain. Okay? Now, if this material is linear elastic and isotropic, then essentially you can use the Hooke's law to replace your epsilon x and gamma x, y, and so on with the stresses. If you do that, essentially you can write the expression for this strain energy Ui simply as a function of stresses. Okay, there are no strains here. Everything is in terms of stresses. Okay, that is nothing but using the Hooke's law to replace the strains by the stresses. Nothing more there. Okay. The one thing I want you to note here is that there is another symbol here which is nu, which is the Poisson's ratio. Okay, it looks similar to gamma, but it's not the same. Gamma is the shear strain, nu is the Poisson's ratio. Okay, they look similar, but they're not the same. So make sure that you know what the difference is. And one way you can always figure that out is nu only comes in relation to sigma, or the normal stress. Okay, so and the shear strain is not related to the normal stress. Okay, so that way you can figure out which symbol is what. Okay, now the one more thing that I want to point out here is that if you look at this expression for ui, you see that sigma x is multiplied only by epsilon x. We know that sigma x also causes an epsilon y and epsilon z. So we learned this when we derived the generalized Hooke's law, right? So sigma x causes both epsilon y and epsilon z. But when it comes to finding out the internal energy or the strain energy, we don't multiply sigma x by epsilon y and epsilon z. The reason is the force due to sigma x is in the positive x direction or the negative x direction, but it's in the x direction. Whereas the displacement due to epsilon y and epsilon z are going to be in the y direction and the z direction, which is orthogonal to the x direction. So essentially, if the force is in one direction and the displacement is perpendicular to it, then that force does not do any work. That is why you don't have a term which is sigma x times epsilon y or sigma y times epsilon z. Sigma y times epsilon y is the only term that contributes to the work done, and the work done is related to the internal energy. Okay, so we have now written ui, the internal energy or the strain energy, in terms of both sigmas and epsilons, or just purely with sigmas and taus. Okay, now you can also write the expression for ui in terms of the principal stresses. Say, suppose somehow you know the principal stresses at every point inside the body. Then essentially you can write the expression for ui just using the principal stresses. And the one thing that is helpful here is that all the shear stresses go to 0. Because when you have a principal stress or principal plane, then the shear stresses there are equal to 0. Okay, but essentially it's just another form or another way of writing this expression for ui, nothing more. Okay, so this is the strain energy in the case of multi-axial loading or a general state of stress. Okay. Now, let's start looking at very specific cases that are relevant to this class. Okay. So in this class, if you think about it, we look at axial loads, we look at bending loads, and we look at torsional loads or the shear stresses due to torsion. Okay. So now let's try to find out what is the strain energy in a body just due to an axial load. Okay. So in this case, what I'm going to do is I'm going to look at a structure like this, like an axially loaded bar, where the internal force at any cross-section is P. And the cross-sectional area is A. Okay. Now, when you have an axial load, and let's assume that this is the x-axis, right? In that case, you are going to have only one non-zero stress, which is sigma x. All the other stresses, sigma y, sigma z, tau xy, tau xz, and tau yz, they are all going to be equal to 0. So in that case, the expression for strain energy reduces to something like this. Okay, so if you go back, this is the expression for your strain energy. And all the other stresses are 0. So only the sigma x squared term remains. Okay. Now, in that case, the strain energy term becomes very simple. It's just going to be sigma x squared over 2e times dv. Now, the one thing that I want you to note is that this dv essentially means that it's a triple integral. Okay? It is not just a single integral, but a triple integral. You're essentially integrating over dx, dy, and dz. Okay? So it is a triple integral. Okay? But now, for this axial loading case though, it becomes a little bit simplified because your sigma x is uniform across the entire cross section, which is nothing but P over A, right? So when you integrate along the y direction and the z direction, the value of sigma x is not going to change. So essentially the integral over dy and dz is nothing but the area of the cross section. Okay? So this triple integral here essentially becomes a one-dimensional integral where the integration is done over just dx. Okay, that's something that I want you to really understand. So if you look at, let me just go back and explain this again. Okay, so this is the expression for ui. Okay, we know that sigma x is nothing but p over a. Okay, so we can substitute that expression into this thing, and that is what we'll get. It's nothing but p over 2ea square times d. Okay, now this is a triple integral, as I told you. Okay, which means that you have to integrate over dx, dy, and dz. Okay, so essentially you have to integrate p square by 2e a square over dx, dy, and dz. Okay, but what is p? P is the force or the internal force, axial force in any particular cross section, which means that it is not going to change with respect to y and z. It might change with respect to x if the cross sectional area changes, but it is not going to change with respect to y and z. So when you integrate over dy and dz, essentially you will get a. Okay, so that is where this a comes from, by integrating over dy and dz. Okay, but now what has happened is that you have taken a triple integral and then converted into a single dimensional integral just over x. So this a that comes from integrating dy and dz cancels off with one of this a's here. So essentially you end up with the expression like this. It is 0 to L of p square over 2ea times dx. Okay, now in a case where the cross-sectional area is also constant, it doesn't vary with x, and p is also constant, the internal force at any cross-section is also not changing with respect to x, then you come up with a very, very simple formula for the strain energy, which is nothing but p square L over 2ae. Okay, so that is the internal energy or the strain energy for the case of axial loading when you have a prismatic bar of uniform cross-section and the internal force is also not changing with respect to x. But in case those things are changing, you can still use this expression to calculate the strain energy. Okay, so that is the strain energy due to the axial load. Okay, it's the exact same way how we are going to find out the strain energy due to bending moment. So I'm not going to go through this in as much detail. The main thing to note is that when you have a bending moment also, there is only one stress, which is sigma x. Okay, so the expression for ui is still the same, except that sigma x is no longer p over a, but sigma x is my over I. Okay, so the expression for bending stress is different from the axial stress, but the procedure is exactly the same. So you put this value for sigma x into this expression, and then you do the integral. And then if you do the integral, you end up with something that is very similar. So the strain energy due to bending is integral from 0 to L of m squared dx over 2ei. And if you just recall what was the strain energy due to axial loading, that was the integral from 0 to L of p squared dx over 2ea. Okay, so that's what I had here, this term here. Okay, so if you look at this term here and that term there, sorry, let me just, and that term there, they actually are quite similar, right? We are still integrating with respect to dx. Instead of p square, we have m square. So instead of the internal force, you have the internal moment. Instead of the cross-sectional area, you have the area moment of inertia I. But if you look at the structure of those two integrals, they are still the same. It's p squared dx over 2ea. In this case, it's m squared dx over 2ei. Right? So they're actually very, very similar. Now, how do you actually go about evaluating integral? So the way you go about evaluating this integral is that you write your m, which is the bending moment, as a function of x. Okay? And that is what you have been doing throughout this class. When you construct this moment diagram, what essentially we are doing is we are finding out what is the moment m as a function of x. So if you know the expression for moment, you put that expression into this integral, and then you evaluate the integral. That's it. And that is how you calculate the strain energy due to bending. Now, if you want to do it, you can try it by yourself, but essentially you can also do the same thing for the strain energy due to a torque, and that is also going to have a very similar expression, right? If you look at the expression of bending, it's m squared dx over 2ei. For the torque, it's t squared dx divided by 2gj. So essentially, you replace the bending moment by the torque. You replace the shear modulus, the Young's modulus, by the shear modulus g, and you replace the area moment of inertia by the polar moment of inertia, right? So all these expressions for like strain energy due to axial loading, bending, and torsional loading, they are all very similar. They have very similar forms, okay? And the main thing that is common to all of them is that the energy is proportional to the square of the internal force or the internal moment or the internal torque, okay? That is something that you must also note, which means that the energy is always going to be positive. Whether the bending moment is negative, or the torque is negative, or the axial force is negative or not, or the internal force is negative or not, it doesn't matter. The strain energy is always going to be positive because you have the square of those values. Okay, so this kind of tells us how to find the strain energy due to different loadings. And we also know what is the work done. How are we actually going to use these two concepts to find deflection? And that is what we are going to look at next. Okay. Now let's think of a very simple case. Say you have a simply supported beam and you apply a force P at the middle of the beam. Okay. Again, you're going to start with 0 force and then slowly increase its value to P. At the end of this process, you are going to have a deflection delta of this beam. Okay. Now, based on what we learned, we know what is the work done by this force P. The work done is going to be half P times delta. Okay. And this force P is essentially causing a bending deformation of the beam. Okay. Now, we know that because it's bending, what is the strain energy associated with bending, which is nothing but this. Right? So now we can write the moment function for this beam, okay, as a function of x and integrate from 0 to L. So you know what the strain energy is, you know what the work done is. Okay? The only unknown in this equation is delta. We know what force we are applying. We know what is the strain energy that is built up in the system. The only thing that we don't know is delta, which means that you can get delta from this expression. The integral of m squared dx over 2ai from 0 to L divided by P. So once you know the strain energy, it is trivial to find out what delta is. Okay, so that is a completely new way of finding out deflections. So if you recall what you would have done in your solid mechanics or mechanics of materials class, you would essentially use the moment curvature relationship. So you would have used this relation something like d squared v over dx square equal to m over ei, okay, where v is the deflection. Okay, so we'll integrate this expression twice and then find out v and apply the boundary conditions to find out v. Okay, this is completely different. You find out the strain energy and then equal it to the work done, and you directly get what the deflection is. The same thing applies when you apply a moment. Say suppose you have a beam like this and you apply a moment m naught, right? And because of this moment m naught, let's say there is a rotation theta of this beam. The work done by this moment we know is half m naught times theta, and that is again going to be the strain energy due to bending, which is this, because the only deformation that is happening in this beam is again a bending deformation, right? So essentially you can equate the work done by the moment m naught with the strain energy due to bending that is stored in the structure, and that essentially gets you theta. Okay, this can be applied for other cases also. In case you apply a torque at the tip of a cantilever or something like that, you know that half t times t naught times phi, which is the angle of rotation at that point, is the work done by the torque, and that is equal to the integral from 0 to L of t squared over 2gj times dx. And same thing applies for a pure axial deformation. Okay, if you apply a force F at the tip of this beam, then half F times delta is the work done by the force, and that is going to be the strain energy due to bending. Oh, sorry, strain energy due to axial deformation. So in all these cases, what essentially we end up doing is that we find out the strain energy due to the applied load, and then equate the work done by the applied load to the strain energy, and that essentially gives us a way to find out the deflection or the rotation or the angle of twist. Okay? So it's a very neat method, but it has some limitations. Okay? The first limitation is that in all these cases, we only had one force or one moment or one torque acting on the body. Okay? What if there is multiple forces acting on the body? Pretty much in every problem you have solved in this class, you always have multiple forces and moments acting on a body, right? So if there are multiple forces acting on this body or multiple moments acting, how are you actually going to find out what the work done is? How do you know how much work is done by force number 1 and how much work is done by force number 2 and so on? Okay? That creates a problem. You might still be able to find out what the strain energy in the body is, but you cannot equate that to the work done by one force or one moment because there are multiple forces and multiple moments. Okay? So essentially, whenever there are multiple forces or moments, you can't use the equivalence between the work done and the strain energy to calculate deflection. That is one problem. The other problem is that in all these cases, we were looking at the deflection or the rotation or the angle of twist at the point where that force or moment or torque was applied. Okay? Now, for example, if you apply a torque at this point, but then you want to find out the angle of rotation at that point, this particular method is not going to help you. Same thing applies for this force. If you try to find out what is the deflection or the extension at that point, some point where the force is not being applied, then you can't find that out. Same thing is true for bending moment. So if you look at, in this case, if you want to find the deflection at this point, delta, you can't find that out. Okay? So this method is actually very helpful, but it's limited. It's limited to cases where there's only a single force or a moment or a torque acting, and you can use this method to find the deflection or rotation or angle of twist at that particular point. Okay? If you want to find out the deflections at arbitrary points in the body, or if you want to look at examples or look at cases where there are multiple forces or multiple moments acting on the body, then you have to use a different method. That method is called Castigliano's method, and that is what we will be looking at in future classes. Okay? I hope that this part at least is clear to you, and we'll take up some examples on this in the forthcoming lectures.